Bismillahirrahmanirrahim. Assalamu alaikum. I welcome you all to the 8th lecture of the course of Control System series. My name is Engineer Jaffar Ali and I am instructor for this course. So, this is the first part of the 8th lecture, and let's start with the recapitulation of the previous lecture. In the last lecture, we have discussed about basically block diagram and the reduction of block diagram and how you can represent a control system in a block diagram, and how can you solve a big block diagram to and reduce it to a single block, so that the single block will have the same effect as compared to all the sum of all these other 9 or 10 or whatsoever blocks. So you can compile this whole control system into a one single block, and the equation for that will be known as a single block diagram equation. And we also found out that how you can calculate or you can reduce the big control system into a single block equation or a single block diagram. So in continuation to that, the second topic that we will be learning today is basically known as the signal flow graph or SFG. So in today's first part, we will look at the introduction to signal flow graphs, the definitions, the terminologies involved in it, and some of the examples of signal flow graphs as well. So as you know that this block diagram method is very good and unique representation of a signal of a control system. Similarly to that, the alternative method to represent a block diagram is known as signal flow graph, and this was developed by someone that is named Samuel Jefferson Mason. And we will learn about the Mason's rule that was produced or proposed by him actually, which is used to find the uh, a single block equation or a reduced form. This rule is basically known as the Mason's rule, and we will look that into also in the coming lecture. That is the second part of this lecture. So let's introduce ourselves to this representation. This the advantage of this representation, that is signal flow graph, is basically you can easily find the gains of the paths, and using that gains of the path, you can easily put the formula, these values into the formula that was proposed by the Masons, known as the Mason rule. So a signal flow graph consists of a network in which nodes are connected by direct branches, and it depicts the flow of the signals from one point to another point on a system, and it gives relationship between the signals as well. So let's have a look at the examples. You can see that in this kind of diagram, the output is basically y. You can see over here that this output is y, and y is nothing but equal to ax. So you can either write this thing, or you can draw a block diagram in which x is input, y is output, this is x is your input, this is block diagram, y is output, and this is your a. So this is mathematical representation, this is block diagram representation, and this is signal flow graph. You can see that signal is flowing from x to y with the gain of b. So this is basically signal flow graph, and each variable in the signal flow graph is designated or designed by a node, and each transmission function of a graph is designed by a branch. So this is the branch. You can see that this is the branch between x and y, and branches are always unidirectional. You can see that these are unidirectional. The signal is flowing from x to y, and the arrow in the branch indicates the direction of the signal flow. So this is a cool representation of a control system as well. Now you can see that there are two examples given over here. There are two equations. Y1 is equal to G11 R1 plus G12 R2. Similarly, Y2 is equal to G21 R1 plus G22 R2. So you can find these values. This is your Y1 and this is your Y2, and these were the inputs R1 and R2. And there were two you can say gains. There are four paths, two for this side and two for this side. So each path has different gain. So this path has a gain of G22, this path has a gain of G21, this path has a gain of G12, and this path has a gain of G11. So the total equation becomes, this is a known as, this diagram is basically a signal flow graph. If you want to find y1, you can easily find y1. You know that y1 is the summation of r2 multiplied by this g12, r2 multiplied by this g12, and addition to that r1 multiplied with this g11, r1 with multiplied with this g11. So this is a cool method. This is again your mathematical modeling, and this is your signal flow graph representation. You can also write, you can either write this or this as well to represent a control system. So this is also another method in which you can write, you can represent your system instead of writing the equations using this flow diagram. So you can see that in this diagram the inputs are these R1 and R2, which is highlighted in the blue color. This R1, R2, and this is the two nodes, that is X1 and this is X2. And if you want to find if you want to find X1, actually X1 is nothing but you can see that R1 multiplied with 1. So R1 multiplied by 1 gives us R1, and this A11 is multiplied with this X2, because you can see that X2 is coming over here and it is multiplied by this A11. So A11 multiplied by X1 by itself, you can see that this is a closed loop, and this A12, this is multiplied by with this X2, sorry. So this is this thing. Similarly, X2, this thing will be equal to R2 multiplied by 1, simply R2, then again A22 multiplied by itself, that is X2, A22 multiplied by itself, X2, and A21 is multiplied with X1 and moved over here. So this is also there. So total X2 will be this and total X1 will be this. So this is again a very common, or you can say very cool representation of a mathematical equation in terms of a signal flow graph. Now there is a more complicated, you can say a bit complicated, not that much complicated but a bit complicated. You can see that this is your X0 is your input, and this X4 is your output actually, and you can see that there are 4 variables involved, that is 4 nodes involved, X2, X1 and X3. These are 3 nodes, intermediate nodes actually. So X1 will be equal to, you can see that X1 is nothing but X0 multiplied with A, this thing, plus X2 multiplied with B, X1 multiplied with B. So X1 is multiplied by B and it's back into X1. You can see that this is back into X1. And similarly, the third thing that is coming over here is this thing, that is C, and it is multiplied with this X2. So this thing becomes the equation for this graph. You can either write this equation from this signal flow graph, or you can draw this signal flow graph using these equations as well. You can go either way. Similarly, this X2 is nothing but D multiplied by with X1. So this this X2 is equal to D multiplied by with X1 and E multiplied by X3, this thing. Similarly, this X3 is nothing but X2 multiplied by G, this thing, and X0, or you can say F2, this X0 multiplied with this F. This is also going to be inserted in this X3. So you can see this is over here, and this total R X4 will be nothing but X3 multiplied by this H. So you have reduced this equation, or you can either draw this signal flow diagram using this equation, or you can either write the equation from the signal flow graph diagram. This is totally up to you. Now let's see another example. You have to construct a signal flow graph for the following set of equations, and it is very much easier to do this. And there are several methods by which you can use this, by which you can draw actually. So this is your x2, and this is this a2 multiplied by x1. So the first thing that you will be letting is x1, and the last thing that you can see is x2 x4 actually. So the input will be x1. You draw this x1 circle, a solid filled circle with x1, and you make x4, that is solid filled x4, that shows the output. And this x1 is nothing, and this x1 is basically the input, and this next x2 is basically the multiplication of a21. This path is basically, you can see that this is a21 multiplied with x1 multiplied with x1, in addition to a23 multiplied with x3. So you have to find a path from x3 to x2 with the name of a23. So you have done this as well. This is your a23. So this is your x2. We have just drawn this from this equation. Similarly, you can draw this x3. x3 is a31 with x1. So x3 is x1 multiplied with this a31 will be inserted in the x3, and again a32 will multiplied with this x2. So this a32 when multiplied with this x2 giving input to the x3. Similarly, this x3 is basically multiplied by itself with a gain of a33. So x3 multiplied with this a33 is went back to the x3 as an input. So this is the equation, and from this equation we have drawn these three lines, this one, this one, this one, and this one, these three lines. Similarly, x4 is nothing but a42 multiplied with x2. So when x2 multiplied by with this a42, you get this x4. So this one line, and again this a43 multiplied with x3. So x3 should be multiplied with this a43, and it should be given to the input of x4. So this is the total representation, and these two lines were drawn as a result of this equation. So using these three equations, we have drawn actually a signal flow graph. This is your complete signal flow graph. Another way to arrange this method is you can use this as well. I have nothing changed anything. I have just adjusted the parameters, and x1 was brought here, x2 was brought on this side, x3 was on this side, and x4 was the output. So you can see that you can also represent or solve or make a very neat diagram as well. This is also right, and this one is also right. These both are showing the same equations. You can check it by yourself. These are showing the same equations that are given to us in the question. Now let's talk about the terminologies that are used or involved while we are discussing this signal flow graph. The first thing that you should know is basically the input node. So this is your input node x1, where the input is given to the system. Output node, or the sink actually, is the one that you should take. You are using at the last or the end of the system, or it has no output branch, it has only incoming branches. And similarly, input node has no incoming branches, it has only outgoing branches. A path is a continuous unidirectional succession of the branches along with no node is passed more than once. So you can see that these are the branches. This one is the branch, this one is the branch, this one is the branch, this one is the branch as well. So this is the branch as well, and this last one. These are the 6 branches. The paths between x1 to x2, x3 to x4, similarly x2 to x3, x3 to x4. These are all the different branches. There is a forward path and a feedback path. The forward path, you know that if the arrow is towards the output side from the input side, this is the forward path, and if the arrow is from output towards the input side, that is basically feedback path. You can see that from x2 to x3, x2 to x3, you can see that this is the reverse path. The arrow is from the x3 to the x2. So this arrow shows the feedback path. So this is your feedback path, this is your forward path, and this x2 x3 back to x3, this is also a feedback path. X3 and back to x2, this is also a feedback path. So you can see that these are some terminologies that we will be using in the lecture as well, while understanding and solving different problems. There is a self loop which I discussed, this A33. This is actually a self loop, a feedback loop, but it is a self loop. And the gain of the branch is a transmission function of that branch. The path gain, you can know that the path gain, these are A42, A21, A32. These are all the path gains. Forward path gain. The loop gain is basically the reverse path gain, that is this A32. Where is it? This is, you can see that is the loop gain, or x22 to x3, and similarly back to x2, A32, and this is the complete loop gain. You can see that this A32 and this A23, x2 starting from the x2 and ending on the x2 as well. You have to find a loop, and you have to find a total loop gain, and the total loop gain will be equal to the product of all the gains that are involved in that loop. So these are the loop gains, and two loops, paths, or loop and a path are said to be non-touching if they have no common nodes. So you can see that we have a loop over here. Let me clear the diagram so you can see it more clearly. These terms will be involved when we are trying to solve it for reduction as well. So you can see that this is one loop, and there is no other loop. You can see that there is no other loop, all are forward paths. And let's say there is a loop, and this loop is something like this, from this x4 to x3 as well. Let's say this is the another loop. So this two will be said non-touching if they do not have any common node, but in this case they have a common node, that is x3. So they are not non-touching, they are touching loops. These loops are touching. Let's say there is another node x5. Let me clear it. Let's say there is another node, and this is basically x5, and let's say this x5 is your output, and there is a loop from x5 to x4. Let's say this is the thing scenario. So this will be non-touching loops. This loop, let's say this is loop 1 and this is loop 2. Now these two loops are non-touching loops. So this is the phenomena. You do not have to have some kind of intermediate or common nodes. If you have uncommon nodes, you can have these non-touching paths. Now consider this diagram, and from this diagram you have to find these several determinants, or you can say the several quantities. The first one, you have to identify the input node. So from the diagram you can see that the input is basically your R of S. The output node is basically your C of S. Similarly, you have to find the forward paths. So the forward paths are from this node to this node, this node to this node. Again, this is the forward path, this is the forward path, this is the forward path, and this is the forward path as well, and this one is also forward path as well. So there are how many paths? 1, 2, 3, 4, 5, 6, 7. So there are 7 forward paths. And the next thing, you have to find the gains of that path. So the gains are G1, G2, G3, G4, G5, G6 and G7. You can see that these are the gains: G1, G2, G3, G4, G5, G6, G7. And the next thing is basically the same as well. This is your first path, and this is your second path. When something arrives, some input arrives at this point, he has two options: either to go this G5 or either to go with the G6. So you have two paths actually, either G5 or either you have to go towards G6. So you have actually two paths, two forward gains, two forward path gains. One forward path complete path gain is this, and one complete path forward path gain is this, because you have two paths. One is a straight line and one is something like this. So you have two paths. So this has this much gain and this path has this much gain. The next thing you have to find is the feedback loops. So you can see that this H1, H2, H3, yes, there are four actually. You can see that this is the first loop. Similarly, this is the second, this is the third in the yellow line, and this complete is as a fourth. So the first loop has the overall function of G2S1, G2H1. The second loop, this loop V3 actually, is G4 multiplied with this H2. Similarly, the third loop, that is in the yellow, you can see that G4, G5 multiplied with H3. G4, G5 multiplied with H3. And the last one is G4, G6 multiplied with H3. So there are four feedback loops. You can see it from the diagram as well. These are the four loops. So the next thing is basically to find the non-touching loop. So you can see that this loop, let's say this is V5, that is G2H1. This is non-touching with G4 H2. This is G4 H2. Similarly, this loop is non-touching with this G4 G5 H3, G4 G5 H3, and this loop is non-touching with G4 G6 H3, G4 G6 H3. All these three loops are touching. These loops, there are three loops inside this, and you see that these have common nodes involved. So that is why these are touching loops. So we are not going to write these. We are only going to write all those loops that are non-touching. So this is a self example. You can have you can do it by yourself. I have also given the solution over here, where you have to find the input, you have to find the output, then you have to write the gains of the paths, different paths, and then you have to identify different paths. Then you have to write loops equations, and you have to find different roots, and you have to find self loops as well. You can see that this is your self loop, x7 to x7 by itself, and at the last you will have to find the gains actually. So these are the gains for the different paths. This A32, let me highlight it. This A32 multiplied with A23, this is the loop gain of this loop. This is the loop gain 4, 3 and 3, 4. This is the one. Similarly, A5 to A4, this is the one. A6, 5, 5, 6, this is the one. And A7, 6 to 6, 7, this is the one. And A6, 5, 7, 6, 5, 7. A6, 5, 7, 6, and again this is the 5, 7. So this is this path. A7, 7, a self loop. A4, 2, 3, 4, 2, 3. Where it is 4, 2, 4, 2, 3, 4, and 2, 3. This is another loop. You can see that this is very much interesting, guys. I have to highlight it actually with the highlighter. So this loop is going forward, and that is how it is coming back. So this is this loop that was I talking about. Similarly, there is another loop in which a 7 to these are involved. Similarly, you have to find these. So these are the loop gains of these feedback loops. So I hope that you have to do it by yourself, and you also have to find the forward path gains as well. And why are we doing this? Because in the coming lecture you are going to see that you are going to witness that using this information that you are gaining from this and these writing these separately, you will be able to solve to find the single diagram or single equation for a complete system. Or you can also write the a single equation of a block diagram or single block using this information, and that is basically known as the Mason's rule, and we will look at that in the coming class. So still sit tight and revise this topic as much as you can, because you know that if you and I will really appreciate if you ask the questions. The more you ask, the more you learn. That's all for the first part. I'll see you in the second part. Thank you. Allah Hafiz.